Welcome again to EET 260. We're going to demonstrate the continuous rotation servo motor. You can see in the document camera here that we have a basic stamp on the Bobot chassis, and we're rotating this motor at some speed in this direction. So let's go look at our code to remember how these motors work. And you might ask, how is this a servo motor? The thing that is servoed in this case, and it's not servoed especially well, is speed. This is not a positional servo. This servo is a more of a speed controlled motor. If you try this with different motors, if you remember from your Bobot, you needed to actually tweak things a little bit to get both motors rotating at the same speed so your Bobot would travel in a straight line. But there is some sort of reference inside the little motor box, and when you give it pulses of a certain size, it will rotate at that speed. And now we have a scope probe here, you can see, and if I take a look at the oscilloscope, I probably don't have the right pin here. Now I do. So let's go look at our program for a second. As you can see, it's rotating at a relatively constant speed there. Our program is it says to servo is pin 12. It's creating a constant name for the pin called to servo. We could have, in our pulse out command down here, we could have put a 12, but this is fancier programming. So we have this definition to say whenever we say to servo, just realize that we're talking about pin 12. So pulse out to servo and then center. This is a number that represents the number of 2 microsecond, you take this number times 2 microseconds and you get the pulse width. Well, up here we have another interesting statement. It says select $stamp. In other words, what kind of stamp do we have? And it says here, select case, if we have a BS2, a BS2E, or a BS2PE. It says pulse out duration units are 2 microseconds for these models, and we do this thing, we defined a constant. Center is con 750. Case BS2SX, BS2P, BS2PX, the pulse out duration units are 0.8 microseconds for those models, and so they have a different constant defined for the name center. We are using 750. We're a BS2, so we're up here using 750, and what we're doing is running an endless loop. Pulse out on pin 12, 750, or basically 1500 microseconds or 1.5 milliseconds, and so that's what the comment here is saying. And then refresh the pulse every 20 milliseconds. So we do this continually, and what we see, I'm going to move our document camera here. What we see over here is a waveform we've seen before, and let me do a little focusing here. Yeah, I guess that's the best we're going to get. We were getting better before, but at any rate, this says 6.7% like it did before. This says 1.5 milliseconds. Remember last time we had like 1.4995, and the frequency is about the same. It's 44 44.9, no, 44.75. So it's almost 45 hertz or 45 pulses per second. And try to hold this steady if I can. You see a little better there. So the way these positional servos work, they tend to work based on this number that you put in the pin. If I change that number, for instance, if I make this number less than 750, so instead of using center, let's use 1200 now. And you can see the motor is moving much faster. Okay, making a lot more noise too, but it's moving faster, and the pulses are fatter. If you look at this, we'll see that we're up above 10. This actually says about 10.3% duty cycle, and 2.4 milliseconds, and actually the overall frequency went down a little bit. That's supposed to be pretty much constant, but the more important thing is the duty cycle. So let's go back to this thing now, and instead of making it that much bigger than 750, let's make it that much smaller than 750. So we've got about 450 on top there, so let's make this a 300 and see what happens. We'll download it, and now you can see it's moving fast like it was, but in the opposite direction. So whatever this feedback mechanism for setting speed is, it's centered around 750, and one can make this motor turn based on the width of the pulses. Now our pulses are, as you can see here, our pulses are I'm focusing. Pulses are very narrow. We're down in the 2% area, 2.8%, closer to 3. Frequencies around 46, almost 47 hertz. Like I said, it really should be nearly constant. But the width is now 0.6 milliseconds or 600 microseconds. So obviously there's a feedback mechanism inside this, the little boxes that these motors are based on. Take this off of here. I think you're familiar from building your Bobot that there's motors in here. There's some kind of mechanism in here that that watches the speed of watches the motor turning and matches it to these to the average value of that signal that you're putting out. Okay. Fatter pulses mean going faster in one direction. Narrower pulses, when you get narrower than 750 or 1.5 milliseconds, then you're going the other direction. And there's a place in these things, unfortunately you can't really see it, but you might remember it. There's a place where you can stick in your screwdriver and tune these so that they're both are going about the same speed when they're both given 750, and so on. So I think maybe they're supposed to go a speed of 0 at 750. How's that? And then they go faster when you use the larger numbers like 1200 in one direction, and they go faster in numbers less than 750 in the other direction, like 300. So if I go back to 750 here, so we'll go back and put in the word center, or we don't have to, we can just put in 750. Whoop, didn't mean to do that. And we download this. Now this person chose to mount their motor so the screw is on that side. I wouldn't necessarily do it that way, but you certainly can. And somewhere in here is like a trim pot that can be set. Now, thank you for mounting those so it's hard to you can see how touchy that thing is. I've got it down to where, so it's getting 750 now, and it's about stopped. All right, so once again, to look at 1200, yeah. So this is 2.4 milliseconds on the pulses, as you remember seeing earlier before, and we're turning in that direction pretty robustly. If I go back, change it to 300, now we're turning in that direction pretty robustly. See, we're going toward the top of the screen. Now we're going toward the bottom of the screen. Just wanted to double check that. And then of course, let's go back and make it 750. And we go to 0. Isn't that great? Okay, so that's the continuous motion servo motor, which is really servoed for speed, not position. The next time we'll talk about, I just happen to have a where am I? Yeah, there we go. I happen to have a DC motor that looks like this, and we're going to use an H-bridge board to run it, and such a board can look like this. This is not the same one as in your kit, but it will. It's an H-bridge, and we'll talk about what an H-bridge is. It's described in your in the L293 data sheet. This one's a little newer part. The TB6612. It has 2 H-bridges in it, but so we'll do a demonstration with that. Okay, until next time. Take it easy and happy motoring.